Well, good afternoon, everyone. Hello there. Welcome to the Academy's Morrison Planetarium and to this presentation of our final show of the day. This is our tour of the universe, which is a little bit different from the other shows that we've been presenting all day. How many of you have seen our other presentations, either Dark Universe or Expedition Reef? Okay, quite a few of you. This show is, again, quite a bit different. It's a live presentation, and it involves a flight through a three-dimensional model of our universe. And so you'll be hearing my voice throughout as I fly us through this model to have a look as we leave the Earth behind, back away from our solar system, and then exit the galaxy and see where we are in the big picture of things. So we'll do that, travel to the edge of the universe, and then come back home to the Academy just in time for closing. So that'll be at 5 o'clock. Because this is a live flight, I'll try not to crash into any stars or fly into a black hole or anything. But because of the immersive nature of the domed experience, the image goes out to your peripheral vision all the way out to the sides. If at any point that makes you feel a little funny, if you're a little sensitive to all that movement across your field of view, just close your eyes for about a minute or so, and that any sensation of discomfort should go away in about a minute or so. As with all of our presentations, before we get underway, we would like to remind you that during this presentation, we'd appreciate it very much if you could please refrain from eating, drinking, snacking, or any kind of photography or recording. This would also be a great time to silence your personal electronics and to tuck away any light-emitting devices such as cell phones, tablets, cameras, flashlights, etc. That light can be very distracting to people sitting around you in the dark and can also interfere with the images that we project onto the dome overhead. At the end of the presentation, we ask everyone to please exit out through the doors at the top of either stairway. Although if getting all the way up these stairs could be a problem for any of you, especially from the lower rows, just stay in your seat and our staff will assist you out the lower exits if that's more convenient. With that, we invite you now to settle back in your seats and make yourselves comfortable. Are you ready for a trip into outer space? Okay, that was pretty good. So we'll go. You know, one famous astronomer once said that outer space is not that far away. It's only an hour's drive if cars could go straight up. Which is true, because we're going to find out just where the edge of space is. And we're going to start our trip right here, 1 kilometer above a place where people usually do go into outer space. We're looking down at pad 39B at Cape Canaveral, which is where a lot of rockets launch from. And we're going to lift off from here. So we'll go from 1 kilometer above the surface to a little bit higher. And as we ascend above Cape Canaveral, we're going to see more of the base here. Pad 39A at the top. Over on the bottom, we'll see the vehicle assembly building just appearing right about there. Over on the left is that 3.5-mile long runway that was used by the space shuttle. And down the coast, over to the right, you see a number of other launch pads and landing zones that are used. And now we're ascending to, we're about 10 kilometers up. We're going to go a lot higher. We're going to go up to about 100 kilometers above the ground. That's about 60 miles. So roughly the distance from San Francisco to San Jose or to Santa Rosa. This is 100 kilometers right here, and this is the internationally recognized boundary of outer space. So this is the limit. Now, why do they use this? Again, about 62 miles, 100 kilometers. It was calculated back in, I think it was about the 50s or so, that this is the rough altitude at which the atmosphere is so thin, because the atmosphere just gets thinner and thinner the higher you go. Up here, at 100 kilometers, the atmosphere is so thin that air control surfaces like wings, flaps, rudders, they don't work. So you have to use rockets to maneuver around. So this is where there's basically no air to work against in terms of aerodynamics. And so this is considered the edge of space, although for different purposes, different agencies still use different figures. And this is not a hard and fast limit. There's no sign up here 100 miles up that says outer space begins here. The atmosphere expands and contracts, and it depends on how much energy it's getting from the sun. Sometimes it's a little higher, sometimes it's a little lower. For a number of purposes, NASA actually uses a lower altitude, 50 miles. But the internationally recognized boundary used by all aeronautical agencies is 100 kilometers. Well, let's go even higher than that, because even though we're on the edge of space, we want to get safely into outer space. We'll go 4 times higher than this. So we'll go up to about 400 kilometers, and that is roughly the altitude at which the International Space Station orbits our planet. So up here is about 250 miles, 400 kilometers. The International Space Station is up here orbiting our planet, traveling at a speed of about 17,000 miles per hour, which is about as fast as a bullet. It circles the Earth once every 90 minutes or so, so it makes 16 circuits around the Earth every day. And this is the farthest that humans currently travel away from our planet. Although about 50 years ago, they went even farther than this. They went about 1,000 times farther. So we're going to go from 250 miles up to about 250,000 miles above the Earth. And so let's zoom away from our planet and go as far as humans have ever traveled, and that is all the way to our nearest neighbor in outer space, our satellite, the moon. Now, to find the moon, I'm going to first turn on its orbit so that we can, we'll see where our target is. So there's the orbit of the moon, and we're going to back off a little bit more. So there's the moon over on the right. We're going to turn in that direction and move forward toward the moon. Now, back 50 years ago, it took the Apollo astronauts about 3 days to get to the moon. We'll get there a lot faster than that, because we don't have the time. We have to do this by 5 o'clock. So, approaching our satellite, this is our nearest neighbor in outer space. You can see it's an object about 2,000 miles across, a bare rock. It has no atmosphere, no water. Although early astronomers used to think that those dark patches on its surface were bodies of water. They called them seas and oceans. But those dark patches are actually large, flat plains of dried lava, which bubbled up from underground, spread out, thinned, and cooled into the plains of rock that you see. The lighter colored areas are covered, as are some of the dark areas, covered by lots and lots and lots of craters. Those craters were blasted out by the impacts of asteroids and comets during the moon's history. And you can't count the craters on the moon, there are just too many. But the International Astronomical Union recognizes about 9,000 named craters on the surface of the moon, but there are a lot more than that. But they come in all different sizes. Some of the bigger ones you see here are about 50 or 60 miles across, and they come even smaller than that. And all that, the result of impacts by asteroids and comets. And we're going back to the moon in the next few years, courtesy of NASA's Project Artemis, which is going to return people to the moon, hopefully, they say, to stay. So we'll see how well that goes. And the next couple of test flights in the next few years will let us know how that's going to go. But let's back away from the moon now and have a look at where we are in our solar system. Now, we've talked about the moon being 250,000 miles away. That's 250,000 miles away. As we travel farther out into space, we're going to encounter objects that are so far away that it's going to take a long time to get there. It took the Apollo astronauts 3 days to get there. It takes a beam of light or radio signals about 1.5 seconds to get from Earth to the moon, which is pretty nice. Get there really quickly. And we'll use that, the speed of light, as a sort of a standard. Astronomers like to use that because it tells them not just how far away things are, but how long it takes for light to travel across those distances. So 250,000 miles, the distance from Earth to the moon, is 1.5 light seconds. If we travel from Earth to other locations, say to other planets, we'll be talking about things that are so far away that they are light hours away. millions and millions of miles. Let's back away from our solar system and have a look. Keep your eye on Earth there, the third planet from the sun. There on the bottom is the sun, our own star, 93 million miles away. That's what we learned in school. And it takes light about 8.5 minutes to travel across that distance. So astronomers say that the sun is 8.5 light minutes away. That's the same thing as saying 93 million miles. And the other planets, we have the nearest planet to the sun is Mercury, and then comes Venus, and then Earth, and then the fourth planet from the sun is the red planet Mars. After Mars comes a big gap. That gap between Mars and the next planet out is filled with a lot of debris. This is material that's left over from the formation of the solar system, and these are called the asteroids. These are typically chunks of rock or metal, and there are a couple of 100,000 of these in this region between the orbits of Mars and the next planet out. Although there are lots of others that cross the orbits of the inner planets, and some cross farther out. So these are just the main ones that we know about, although there are others called near-Earth asteroids and different classifications of asteroids that are distributed in other parts of the solar system. After the asteroid belt comes the giant planet Jupiter, which is the first of the Jovian planets, or the giant gas planets. The four inner planets, Mercury, Venus, Earth, and Mars, are rocky, and they're smaller than the giant planets. Jupiter is really big. Jupiter is about 11 times as wide as Earth. The next planet out, Saturn, is about 9.5 times as wide as Earth. And then the last two giant planets are Uranus and Neptune. They're called the ice giants, and those are each about 4 times as wide as Earth. So those are the 8 planets of our solar system orbiting our star, the sun. Now, one other thing we do want to point out to you is that there's another region, another belt of debris, kind of like the asteroid belt, surrounding the outer planets of the solar system. And this area is sometimes called the zone of trans-Neptunian objects, or also known as the Kuiper belt. It was first predicted in the 50s by an astronomer named Gerhard Kuiper. And he said there's probably a lot of junk out there in the outer solar system. And he was right, because astronomers have now begun to find more and more things out here. And among them, one which was found in 1930 was what we used to call the planet Pluto. But now there are other objects out here, so many other objects, that a lot of astronomers say that Pluto can't really be considered a planet like the others, because it's fairly small, and it hasn't used its gravity to sort of bully these other little objects out of its orbital path. And so with so much junk in the same orbital path, astronomers say it's got to be a different kind of object. So they say that objects out here in the Kuiper belt, some of them can be called dwarf planets like Pluto, because they're roughly the same size as Pluto, some a little bit smaller, but there are lots and lots and lots of other things out here. Lots of comets as well, these short period comets, and there's another belt that's even farther out than this. That's where the long period comets are. But as far as the immediate solar system is concerned, this is about the outer limit of it. One other thing that I do want to point out to you is how far out some of our spacecraft have gone. We talked about how the Apollo astronauts went to the moon, and how we measure the distances to other planets in the solar system by the speed of light, the distance to the sun, the distance to Mars and other objects. I'm going to show you the paths of our most distant ambassadors from Earth. These are the spacecraft that have been traveling away from Earth since about the 1970s. One of them, traveling off by itself over to the left, is the Pioneer 10 spacecraft, and then going off in the other direction is Pioneer 11, which was launched about a year or two later, and then the 2 Voyager spacecraft, Voyager 1 and Voyager 2, and then the last one is New Horizons, which passed the planet Pluto not too long ago. Those are the 5 spacecraft that have left the solar system. They have all passed the orbits of the most distant planets, and are continuing to travel farther and farther out into space. Those are our most distant physical emissaries. But there's something else that's even farther out there that is still evidence of our existence in the universe. I'll point that out to you in just a bit. As we continue traveling farther and farther out from the sun, however, far away from our solar system, we'll enter the area known as interstellar space. This is the space between the stars. And now we're talking about objects that are so far away that their light takes years to reach us here on Earth. The nearest star to us, Alpha Centauri, is about 4 1/3 light years away. That's about 6 trillion, 25 trillion miles. A light year is the distance that light travels in 1 year. Should explain that. And that's about 6 trillion miles. So every time I say light year, just multiply that by 6 trillion, and that's the number of miles that I'm talking about. But as we travel farther and farther out, now we're passing through the stars, and so our perspective is changing. Our point of view is changing with respect to where the stars are all located, and so the constellations become less recognizable way out here because we're not seeing the stars from the same angle as we do from Earth. But out here, I want to point out one more thing to you, and that is the most distant evidence of our existence in the universe. This is where our radio signals have traveled. This giant bubble is as far out as radio signals have gotten. For the past 90 years, we've been broadcasting radio signals into the universe, some accidentally and some on purpose, and they've only gotten this far, about 90 light years out. Now you can see that there are actually some stars within this radio footprint. So if there's anybody there on a planet orbiting one of those stars, they might have heard our radio signals. Anybody else outside this radiosphere has not heard us yet. And so they wouldn't know that we're even here in the universe. They don't have any existence of us yet. So that's our radiosphere. We'll leave that on just to mark our location in the Milky Way galaxy, because we're going to continue moving farther and farther out. And we'll back away from our giant family of stars, the Milky Way. Now, up until about 100 years ago, astronomers thought that there was only one galaxy in the entire universe, the Milky Way. And then Edwin Hubble, you might have heard that name before, but Edwin Hubble pointed out that there are other galaxies farther outside the Milky Way. Not only that, not only are there other galaxies, but the galaxies are all moving farther and farther apart. Not only was the universe bigger than we had thought before, but it's getting even bigger still. Our own Milky Way is a large, flat disk of several hundred billion stars. It's about 100,000 light years across, so it takes a beam of light about 100,000 years to get from one edge all the way across to the other. But it's this large flat disk that you can see. We are located not at the center of the galaxy, but about 2/3 of the way out from the center. There's our radiosphere. That's where we're located, right on the edge of one of the spiral arms. Now, the Milky Way, again, is not the only galaxy in the universe. It's a member of a small cluster of galaxies, about 80 galaxies by some estimates, and these are the nearest galaxies to us. And now that we've left the Milky Way, every spot of light that you see here is not a star, but is actually a distant galaxy. And this is all based on real data, real information based on surveys of the universe that have been made over time. So as we back away even farther still, you can see that not only is our Milky Way a member of a cluster of galaxies, but lots of other galaxies are members of clusters of their own. And some of these clusters are huge, containing thousands of galaxies. These are called superclusters. And as we back away even farther still, we see that there actually is a texture to the universe. The way the galaxies are distributed looks like there are chains of galaxies, or filaments separated by large empty spaces or voids. And if we travel even farther out still, far enough away to see this picture, this is our current map of our immediate part of the universe, most of the universe actually, and you can see the different colors here, which are representative of the different surveys that have been used to map out the galaxies. So the galaxies are not really these nice pretty colors, but if we back away even farther still, we'll see something else very interesting about our current model of the universe. This is the distribution of known galaxies, and from certain angles like this, it looks almost like the galaxy is, or the universe is shaped like a big bow tie or a giant butterfly. Is this really the shape of the universe? Well, no. The reason this empty space here off to the sides, these dark areas between the two large fans that go off in opposite directions, those large areas are not empty space. They're just areas that we haven't mapped well enough yet because we can't see those areas very well. There's something blocking our view. And what's blocking our view is the dust and gas along the plane of our flat Milky Way. This is the orientation of the Milky Way along this plane right here. And so all the stuff that's in the plane of the galaxy is preventing us from seeing what we are pretty sure is out here, lots and lots of other galaxies. So eventually, as our techniques and technologies get better, we expect to be able to see more out here. We've begun to survey some of the galaxies closer in, as you can see in this little bit of data, but eventually we do expect that our map of the universe will be much more uniform in all directions. We just have to give it some time and let our technology develop a little bit more. As we travel farther out, the most distant objects that have been detected are things called quasi-stellar radio sources, or quasars for short. These are very, very distant objects that are also very, very bright. And to be as bright as they are from the tremendous distances where they've been located, they're represented by the orange dots that you can see there. That's in the neighborhood of about 10 billion light years away. So the light of the quasars has taken 10 billion years to reach us here on Earth. These objects have to be tremendously energetic. And what astronomers believe, at least one theory for what quasars might be, is that they are newborn galaxies powered by supermassive black holes. And it's believed that almost every large galaxy has a supermassive black hole at its center, including the Milky Way. And this is almost as far out as we've been able to detect anything, but there is one last phenomenon that has been detected, and that is something that permeates the entire universe. It's a faint radiation that comes from all directions in the microwave region of the electromagnetic spectrum. It's something that has come to be known as the cosmic microwave background. And this radiation, which surrounds everything, comes from all directions, is believed to be the lingering echo of what's called the Big Bang, the time when the galaxies began to expand away from each other. At one time, it's believed that the entire universe was very hot, very dense, very opaque, and then it suddenly basically changed its state, became very transparent, became very cool, very rarefied. And that is when the galaxies began to expand away from each other. And at one point, the opacity of the universe became so thin, became so transparent that light could actually travel from one place to another. Before, it couldn't. But then it eventually was able to. And this is the first light that was able to travel across space. Now, what we're seeing is not a map of actual light, but rather it's a temperature map of the very, very young universe. It shows where some areas are a little bit hotter and a little bit cooler. And it shows the beginning of the differentiation of matter and the beginning of the formation of stars and galaxies. So this is as far out as we've been able to detect anything. This is as far out as we can collect any data about the universe at all. With that being the case, there's no place else for us to go except back to where we came from. So as we travel farther in, let's think about a couple of things. This is our current model of the universe, which tells us that we still have a long ways to go. We still have a lot to learn about the cosmos because there's a lot of missing data. But there's also the fact that a lot of the universe is stuff that we still can't really detect. About 95% of the universe is not visible to us. We have to use different means, not optical telescopes to detect them, not radio telescopes. We have to use some other means, and that's something called dark matter. It's believed that about 75% of the universe is composed of dark matter. Then there's something else that is causing the expansion of the galaxies to accelerate, which astronomers can't explain. And for lack of a better term, they call that dark energy. So there are several things that are still very, very mystifying about the universe. Its size is just incomprehensible. The number of galaxies that we see is just amazing. And considering the number of galaxies we see and the number of stars that are in each galaxy, billions or even trillions in some cases, it makes you wonder how many stars are there in the universe. And around those stars, how many planets might there be orbiting around them? Have we discovered other planets orbiting distant stars? The answer is most definitely yes. Since about 1994, astronomers have detected planets orbiting stars other than the sun. And if we can turn on a little chart, or rather a plot of the extrasolar planets that have been detected so far, this is what we come up with. Now again, this is based on real data. These are the locations of stars that are known to be orbited by planets. And so far, since about 1994, astronomers have detected more than 5,000 other planets way outside our own solar system. So are any of those planets anything at all like the Earth? Well, we just don't know. And what does like the Earth mean, really? I mean, there are some that are about the same size. There are some that are rocky. Do they have life on their surfaces? That we don't know. And we do know that it takes a certain number of circumstances for life to be able to evolve and thrive on a planet. The planet has to be the right kind of planet. It's got to have a good solid surface for things to develop. It's got to orbit the right kind of star that doesn't give off a dangerous form of radiation. It's got to be the right distance from the star, so it's neither too hot nor too cold. And there have to be a lot of other conditions that must be met. The planet has to be made of the right kind of stuff so that it has the nutrients that can sustain life. So there are lots and lots and lots of special conditions that need to be met in order for us to say whether or not a planet can support life, and therefore whether a planet can be considered Earth-like. So that being the case, with as little as we know so far, in our travels through the universe, from the Milky Way out to the edge of the observable universe and back, past all the billions and billions of stars, past the 5,000 and more planets that we know exist out there, we find that there is quite literally no place like home. There is nowhere else in the universe, as far as we know, where life can exist just yet, but we're still looking. And with that, welcome home. Welcome back to the planet Earth, and thank you much for joining us on our tour of the universe. As the lights gradually come up, just take a moment or two to check around your seats and make sure you're not leaving any personal items behind. As you exit the planetarium, just turn to the right and cross the two bridges that lead to the elevators or the stairway that'll bring you back to the main floor. Once again, thank you all very much for joining us, and we hope you enjoy your evening.